Hi, my name is Sumit Dahal, and I'm a graduate student at Johns Hopkins University in the Department of Physics and Astronomy. Today, I'm going to talk about a paper I submitted in SPIE proceedings and is also available in archive through the link shown below. This was a collaborative work done with my colleagues, especially at Johns Hopkins and NASA's Goddard Space Flight Center. I would like to start with a brief background on the CLASS telescope. Our standard model of cosmology, also known as lambda CDM, tells us how the universe expanded and cooled from a hot and dense state. The simulation you are seeing here basically packs the 14 billion years of our universe's history in 30 seconds. And our current observations match these predictions pretty well. However, what our standard model does not tell us is what happened right in the beginning, what seeded the formation of large-scale structures as the universe evolved. So let's rewind back to t time equals 0. This is the time when the entire universe was smaller than the size of an atom. This is where CLASS comes in. CLASS is going after the most fundamental question: how did it all begin? The leading theory is a period of exponential expansion called inflation, an early universe that magnified quantum fluctuations to cosmic scale and seeded the large-scale structure formation. What you see here are those fluctuations in the earliest light of the universe called the cosmic microwave background, CMB. This particular map was created after 9 years of survey from the WMAP space satellite. So how do you actually test inflation? The exponential expansion would emit primordial gravitational waves that would leave an imprint on the CMB. These gravitational waves would produce a pinwheel pattern on the polarization of the CMB. So a detection of pinwheel pattern would be an evidence for inflation. Now I will talk about how CLASS aims to detect inflation. CLASS is an array of 4 telescopes located in the Atacama Desert in Chile, 17,000 feet above the sea level. From here, we can survey about 75% of our sky. Why do we have 4 telescopes? Because this is what we want to see, a polarization in the CMB. However, this is what we see. This is a Planck satellite's map at 100 gigahertz. This is due to the contamination from galactic foregrounds. One of the main challenges to detect primordial gravitational waves is removing the galactic foregrounds from our map. In our case, mainly dust and synchrotron emission. That's why CLASS has 1 telescope at 40 gigahertz making the synchrotron map, 1 dichroic telescope at 150-220 gigahertz that maps the dust, and 2 telescopes at 90 gigahertz that is optimized for CMB observation at minimum foreground emissions. Here I show you how we survey the sky. Every day our detectors scan 75% of the sky as the sky moves over our telescope. One of the things that make CLASS unique are these very high sensitive detectors that look at the sky. And these detectors are the main focus of my paper. Here I show you an image of an array of 90 gigahertz detectors that we recently deployed. Our detectors are made from superconducting bolometers that operate below 150 millikelvin. To achieve this low temperature, we mount our detector array inside a cryostat that is cooled by a helium dilution fridge and backed by a pulse tube cooler. Combinedly, these fridges can cool down the detectors down to 28 millikelvin, which is very close to the absolute minimum, absolute zero temperature. This exploded view shows what is inside the array and how we stack them. As the light comes in through the smooth wall copper feed horns, it goes through the base plate made from a special alloy of silicon and aluminum, and the light goes to the detectors, which is then read out by the readout circuit right beneath it. Each of this module consists of a silicon detector wafer with 37 detectors that are sensitive to 2 orthogonal polarizations. A unique thing about class detectors is that the detectors are fabricated on a single crystal of silicon for detector uniformity across the wafer. If you were to zoom in on one of these detectors, then you can see our detector circuit architecture. Here you can notice the 2 orthogonal antennas that detect 2 linear polarizations of the light, and through the microcircuitry it directs the optical signal to the bolometers. If you were to zoom in on one of these bolometers, you will see how our bolometers are designed. Before fielding, we extensively tested these detectors in lab. We tested for the detector parameters by keeping the detectors at various temperatures, and we checked for the uniformity of detector parameters throughout the wafers, and we concluded that the detector parameters are uniform and are within target margins. We also measured the bandpass of our detectors to make sure that they agree with our simulations. Finally, we measured the noise spectra of our detectors to make sure that our detectors do not have a higher noise than our background. So the 3 main take-home messages from the paper is that our detector parameters are within target margins, our bandpass is spot on, and our detectors are background noise limited. Thanks for watching. The link to the paper can be found in the description, and please stay tuned for the exciting CMB data. Thank you.